Awesome. All right. Welcome, everyone. Okay, this is going to be our first part of our OpenRocket workshop. We will be having a second Rocket workshop, and that will be tailored more specifically to you guys getting your hands on the program and actually using it. So this workshop, we're just going to kind of provide the bare bones, like what it is, the main tools that it has, and also we'll be going through an example together as well. So yeah, let's get started.
Cool. So for those of you who aren't familiar with the software, OpenRocket is a rocket simulation software, and it's all open source. It allows you to design various components for your rocket and edit properties such as mass and material finish, that kind of stuff. And you can also simulate launches, which you can see at this bottom right photo. So it's quite a powerful software and it's quite easy to use. So don't be too scared. And here's an example of what you can do. You can set up even a 3D model and by adding various parts to your rocket. And here's a closer view at a simulated launch. You can see we're simulating the altitude that the rocket flies to and the velocity, acceleration, and various events during the launch, such as the motor burnout and the apogee at the peak here, and also recovery device deployment, which means parachute deployment. So there's a lot you can do.
Okay, so first off, what we're going to do is I've sent the link on the chat, but for the ones that haven't had OpenRocket downloaded it yet, open up the link and press download for the blue button for the version 15.03.
So just here. And when you download it, you'll get this jar file. And that's all you need to do on Windows. You just go to the location of that jar file and double click on it. That's pretty easy on Windows. Apparently it's more difficult on Mac. If we have any Mac users, we'll troubleshoot with you later on that. But yeah, this is the software. And hopefully you've all pretty comfortable with downloading that. So, sorry, Anne, you continue.
No, all good. That was good. Yeah, so once you've got that downloaded, just click on the GitHub link. I'll send you guys the link very soon. And in that, there will be a demo rocket that you can download, which comes as an ORK file. When you navigate in OpenRocket, you just have to click File and then Open, and then you click the ORK file to be able to open it. Yeah, so I'll send you guys the link to that as well, and probably maybe we'll give you guys like a few, like couple of minutes just to have that downloaded and to download the demo as well. And if you've got both of those things done, maybe like give us a thumbs up on the chat.
Yes.
Okay, so
you just go here, click at the bottom corner here, Demo Rocket. And there's a little download button to the right of your screen. And once you've downloaded that, it'll be called demorocket.org. To open it in OpenRocket, just do File, Open from within the software. And navigate to wherever it is, Documents, Demo Rocket. So this is an old redundant design that we're no longer using for Project Phobos, but it demonstrates a lot of the features. And if you've already downloaded it, just have a browse, have a look, click on some of the different components. And Hassan just sent some troubleshooting instructions for Mac and Linux users for installing the software. But yeah, you can have a look at the 3D view, mess around with some properties, double click on a body part or on any part to look at the properties, look at the material. We're going to cover this in more detail. But yeah, just give us a thumbs up when you're ready and we'll...
Maybe give us a green check mark because the thumbs up just goes away after a little while. So
Okay.
check
Yes.
green check mark.
Nice.
Check the list off. You too, Hassan. You count.
Does this block... Can you see the participants box? Is that blocking anything on my screen?
No, it's only OpenRocket that's sharing on your screen.
Okay.
Unobstructed.
Perfect. All right. So I saw heaps of thumbs up there. Ticks.
Yeah, 6 people. I think that's
Yep.
pretty good.
Edwin, are we still downloading for you or all done? I think that's one of the few people I didn't see a tick for.
OpenRocket downloaded is what Edwin
Perfect.
said. Cool. Awesome.
All right. So let's move on. Let's move ahead. And yeah, if you're struggling, just send us a message in chat and we'll help you while we're presenting. Someone will be available to help you.
Yeah, got a couple of experienced people here. Awesome. All right. Just maybe untick now that you've ticked, and we're going to go to the next slide. Okay, so to get started from how Cas has demonstrated, we can go on files and then new, and that will open up a whole blank new project for you to work off of. So just to kind of get familiarized with what all of this is, we've got the components menu on the right hand side. That's where we will have all of our tools, like such as the nose cone and all of the body structures to build our rocket. On the left hand side is kind of like your builder area. So this is where you're going to drag and drop those components into to start building your rocket. And then that components view at the bottom will just kind of show you physically what the rocket will start to look like. And it also gives you some very useful information that we'll get into detail later. So first of all, so just make sure that you've got the sustainer over there, which kind of indicates where the parts of your rocket that will be kept after deployment. So if you're working on a multi-stage rocket, you will have to add on to a new stage, and that's in that new stage button over there.
Ah, new stage button is just there for those of you who want to make a multi-stage rocket, but we'll be using single stage.
Yeah.
So for now, sustainer is fine. That's just the stage that will remain. Yep.
Awesome.
So once you've created your new file and you've got a sustainer, we can start adding our first parts. So the first part we want to add is a nose cone, and it's under the components menu here, and you can drag and drop it to the sustainer branch. And when we double click on it in the sustainer, which I'll show you. So if we drag and drop to there, I'll just double click. When we double click on it in this menu, it comes up with all the different options that we have. Okay. And you can mess with the shape. You can mess with the dimensions, how long it is, how wide it is. You can do whatever you please and just choose whatever shape and size you want. One important thing for building our rockets is we're going to be 3D printing the nose cone. So we want to convert the component material for the nose cone to this material, polycarbonate lexan. So I'll show you where that is in the software. We go here to component material, scroll down a bit, and polycarbonate lexan. We also want to change the component finish to unfinished because regular paint is the default option, but we won't be painting our parts. We'll just be 3D printing them. So 150 micrometers. And those are the two settings that we need to keep consistent for everyone's designs, but all the other settings, edit them as you please. And that's the nose cone. I think that's all we needed to say for the nose cone.
Okay, awesome. So for the body tube, you just have to drag and drop that underneath the nose cone. The same as how the nose cone was done, you can set the material to what you want. So in this case, we can build a body tube made out of cardboard if we wanted to, and making sure you've got that unfinished finish as well. Just so nice. Yep. So from the body tube, you can add components to that body tube. And as you can see on the new component section, you can add fins if you wanted to. So there are 3 types that you can add. And you can also add things within the body tube, such as like inner tubes and parachutes, and even bulkheads and centerings as well. So definitely mess around. All you have to do to put a fin on a body tube is drag that fin and then drop it underneath the body tube.
Drag and drop isn't working on my computer, so I'll just click on it.
Okay.
If you click on it, it works. So for the fins, once we've attached the fins to our body tube, oh, actually, we need to add a second body tube, which will be the rear body tube. And that rear body tube is just at the little short bit at the back here. That's going to be 3D printed as well, so that we can 3D print the fins and this bit together. But the middle will be cardboard or whatever material you want to use. So I'll just go back and I'll add a second body tube before I add the fins. So here's the second body tube. I'm going to set this second body tube to the same material and finish as the nose cone because it's 3D printed. So polycarbonate lexan and 150 micrometers. I'm also going to set the length to a little bit shorter. This is just the rear component. All right. Now we can click on that second body tube and add the fins, as Ann was saying. And there are heaps of options for the fins. So let's look at the fins slide. Oh, there's no fin slide. Sorry, I'll just do it in the software. So there are heaps of different options. We can adjust the number of fins that we want. Generally, more fins is more stable. However, we're typically not going to go above 4. Just a message in the chat. The red and blue dots, we'll be getting to that very soon. That's
that
the
will be
next slide.
The next slide.
So hold on to your hats.
Good question, Jack.
So we can adjust the fin rotation. And I'll go into the 3D view just to give a better visual of what these settings do. So fin rotation is just rotating around the body. We'll just keep that at 0 for now. This setting adjusts the angle of sort of longitudinal rotation. You can see it's sort of spiral shaped.
Twist, yeah.
Twist, yeah. Again, we're not going to really mess with that. We'll just stick that to 0. Root chord is the length of the fin that's right against the body. It's this length here. So if I increase that, you can see that the chord adjacent to the body changes in size. The tip chord is the opposite end of the fin. It's this far end. So let's reduce that in size a bit. Maybe set that to 1.5 centimeters. See how that looks. So that's what the root and tip chord means. The height is really the width of the fin. So if I increase that to 5 centimeters, you can see they get wider and wider. I have found, and Ben will be able to give more information on this next week, I've found that increasing the height of the fins tends to increase the stability. The sweep length is the length, it's the length from this point where the fin attaches to the body, the leading edge, to the leading edge over here at the tip chord. So that's how far it sweeps back. Okay, so mess around with that setting as well. And then the sweep angle is just another version of the exact same variable. It's just in angle. It's the angle of this line instead of the distance. So these two settings are intertwined. And again, I'm going to set the component to polycarbonate, Lexan, and 150 micrometers because we'll be 3D printing the fins. Okay, so mess around with the fin settings and get them however you like them. Now to the question in the chat, what are those dots? Anne, take it
Yeah.
away.
Okay. So what these dots mean is basically our center of gravity and center of pressure. So that blue dot indicates the center of gravity. Just a revision from what we talked about last week. The center of gravity is the point at which we can say is the center of all mass. And it can also be thought of as a pivot point where any force acting on the rocket, that kind of is the point of where it will be spinning or torquing. The center of pressure is if you can think about all the forces that all the pressure forces that act on the rocket, if they were to be all summed up, where its respective centered location will be, that's the center of pressure. So in flight stability, we mentioned this before, but usually you would want your center of pressure to be behind your center of gravity. And the best practice is to be 1 or 2 calibers behind the center of gravity. Calibers meaning the diameter of the body tube. So you would want that to be 1 or 2 diameters behind the center of gravity. The reason behind all of this is to do with the fact that when forces act on the rocket, when the center of pressure is behind the center of gravity, it can help restore the rocket back to its aligned angle. When it's in front, it ends up kind of exacerbating that kind of wind or disturbance, and so you'd end up with a very unstable rocket. So if you see on the screen on the right hand side there, you've got your center of gravity and center of pressure, and it tells you exactly its location on the rocket.
Right.
All good. And it's also got the indicator of your stability as well. So it's in CAL, and usually, like we said before, you'd want it to be within the range of 1 to 2. So 1.3 to 2.5 is kind of like the range of stability that we kind of look for when we're designing a rocket. So this is a really good indicator for us as we're building our rocket to see in practice how stable our rocket is. And it's kind of something that you should kind of keep a tab on as you're building your rocket.
I will quickly mention as well that the stability number there is for like just a fixed velocity. I think the standard is like Mach 0.1 or something. So, you know, pretty fast. When we go further into the presentation, we'll have a look at more detailed simulations that tells you the stability over time, because it is something that changes with velocity.
Yeah,
Yep,
awesome.
Very
Thanks,
good
Ben.
point. So you can see, perhaps it's a bit difficult to see. I'll go back to the slide. You can see at the bottom in gray, it says at m equals 0.3, so at Mach 3. And as Ben said, change the velocity, you're changing the Mach value, that's going to change your stability value. Okay, so in this case, stability is 2.17, which is quite high, and it needs to be within this sort of range. And I'll just quickly demo. If you can see that stability value there, let's say I reduce the height of my fins, stability values changing dramatically. Okay, so all of these different settings will change that stability value. What's up next? Motors. Okay, so the next thing to do is to add a motor to our rocket design. We add this to the body tube, and we actually go to a different tab in the software. We go to this Motors and Configuration tab, which is step 1. Then we select the body tube that we want to add the motor to, which is step 2 here. And then click New Configuration at the top and select this motor mount. And then press 5. Press select motor, step 5, to actually choose which motor we're going to add. So let's see what that looks like in the software. I'm going to select this rear body tube, Motors and Configuration. Again, I'll select the rear body tube. And I'm just going to move this down because I can't press it in Zoom. I press New Configuration, select this motor mount, and then press select motor here. And there's going to be a big list of motors that we can select from. All right. And in terms of selecting the motor, we're going to provide you with C65 motors. Okay. So we're just going to give those to you. And the C refers to the thrust class. Okay. ABC all the way up to O in this software, and the later in the alphabet, the letter, the more impulse we have. Okay, and we're going to go to C, then we're going to go to C6, which is the average thrust, and you'll see in the menu there, it'll say C6. And up the top, we've got the ejection charge delay, which we're going to set to 5, and that will give us a C65 motor. All right, and the ejection charge delay just refers to how long we'll coast for before we'll fire the ejection charge towards the front of the rocket, which will pop the parachute out. It will pop the nose cone off and release the parachute. Is that right, Ben?
Correct. Yes,
Okay.
Absolutely.
Perfect. All right. So let's go back to our rocket and select total impulse to C. And I can see, where's a good C6 one? There's a C6 under this designation column. And we can set our ejection charge delay to 5. So that is a C65 motor. Press OK, and voila. It's actually added the motor there. And that adjusts the stability, the center of pressure, the center of gravity. It adjusts all of those values. So you'll need to keep track of those anytime you add a component. All right, so that's how to add a motor. In particular, the motor will be providing you the C65. That's just the same slide. That's just demonstrating what it looks like. Anne?
All right. Yep. Okay. So now it's time to kind of add in the parachute. We're going to use that same principle as how we kind of added our fins into it as well. But this time we're going to be placing that parachute in the upper body tube, or the one closest to the nose cone. In this one, we're going to say that the parachute is roughly 15 centimeters. Obviously, it depends on the rocket you're building and how big it is and how fast it's moving. So this is just kind of like an example that we'll be putting in. So if you open up, cool.
Yep.
And just that upper one, drag or double click the parachute.
Mm-hmm.
Awesome. And then just
here, wasn't it? So this slider position relative to top of the parent component, i.e. top of the middle body tube. And if we slide this, put it somewhere in the middle of your body tube. And then packed length is the 15 centimeter value that we were referencing. Recenter it. So this rocket's probably a little bit too short and stumpy. You probably want to increase the length of the body tube, but that's easy enough. Let's say I'm using like a Glad wrap cardboard roll or something like that. That's roughly, I don't know, 32 centimeters or something. And that seems to improve our stability value a bit. It's going to increase the length of the nose cone slightly as well. And recenter the parachute. So that's how to add a parachute. And we're getting pretty close to looking like an actual functional rocket now, at least a very basic one. And what's up next? Anne, did you want to?
Yeah, awesome. Yeah. Okay, so now that we've kind of got a rocket, you can always iteratively run simulations just to see how it performs along the way. So if you go back to the OpenRocket and we go to flight simulations at that top tab and we create a new simulation. Here we can adjust some settings. On launch day, we can kind of set the particular location, such as the longitude and latitude, and also the altitude as well, because those are important informations to give us indications of the air, like density and things like that, which would influence the flight performance. But in this case, let's just pretend that we don't really know where we are flying it. So we're just going to keep it as what it is. And you can also set wind speed settings as well. So say it's a super windy day, or you want to plan for the worst case scenario, you can increase that wind speed up and run the simulation to see how it performs in different conditions. So let's just say for now, we just kind of keep those settings as is, and we simulate and plot it. And just click plot. And here we've got ourselves what the what the flight trajectory would look like. So that red line shows you kind of the trajectory of the parachute. So as you can see, it flies up, it reaches apogee, and it kind of descends down a bit before you see that blue line, which indicates parachute deployment, and that's when the parachute deploys and it would kind of fall down. Ideally, you want that parachute deployment to occur after apogee, but you don't want it to occur too late, because then, you know, if it's deployed too late, then it won't have time to slow down and it'll just crash. So it just has to be at the right sweet spot. And with all of that, you can just adjust the parachute and the motors as well to kind of suit that. Yeah, the blue line indicates your velocity, and also that green line there kind of shows you the acceleration. You can see just when the parachute deploys, there's like that spike in acceleration, which kind of makes sense because that initial shock from the deployment of the parachute kind of like obviously accelerate the rocket a little bit.
Yep. Perfect. I'm just curious, Ben, do you have any feedback for this particular launch?
Yep. So we can see here that the recovery device, as Anne mentioned, is deploying a little bit late. So you generally want it sitting around half a second to 1 second after apogee, whereas here it's sitting closer to 2 seconds. But that just means we need to have a bit of a look at our design and see where we can basically reduce the weight of our rocket or reduce the drag of our rocket to make sure that it spends, it spends more time going up, so it has a higher apogee. So therefore, the apogee is closer to the time of the recovery device deployment. Which might be something you want to do now and sort of show how it's an iterative, like, a little bit of trial and error, you might say, to actually designing a rocket. So we see here that, our apogee is not high enough. So how would we go about remedying that?
What would you recommend then, Ben? Let's go through a bit of diagnosis here. What should we do?
Okay, so first thing that sort of springs to attention would be the fins. We can probably reduce the drag of our rocket by making the fins more angled. This may reduce the stability, but we'd probably reduce the height of the fins to what we sort of can afford to, and then increase the root chord, bringing the base of the fins forward.
How does that look?
Okay, excellent. So we can see, if you just give us a bit of, if you close that menu and just give us a bit of Control Z and Control Y, we can see now our apogee is 89.8 meters. And before, with the previous fins, you just Control Z. Okay, so we've given us an extra 2 meters there. So if we go back to the fins after modification, good. So we've given us a few extra meters there for. Yep.
Sorry, just to let everyone know where Ben's reading off, it's that bottom left corner where it says apogee. It kind of gives you that quick information that you need. Sorry, yeah, continue, Ben.
Exactly. No, thank you. And then as well as that, we can definitely look at reducing the diameter of our rocket a little bit, because, radius of a circle relation to the area of the cylinder, the lower the surface area of the rocket, the lower its drag. So if we have a look now, just reducing it by 1 centimeter has reduced the surface area by so much the drag is decreased enough to give us an extra 30 meters of apogee. So if you want to sim that up real quickly.
Yep, so that's beforehand 90 meters. Now it's 120 meters.
Yep. So sim that up and we'll see how our timing is looking. Beautiful.
Hey, what do you know?
Hey, remedied. Thank you, Ben.
All good. So yeah, and you can see also that reducing the diameter of the body increased our stability by quite a bit. If you can see on the top right of the sort of simulation little thing there, like we're up at near 2 stability calibers, where before we were only 1.2 with the thicker body. And that's, partly due to because the surface area towards the front of the rocket was decreased, our center of pressure is more influenced by the fins, so it's further towards the back. Center of pressure being, where the surface area in the front and surface area behind are equal, because it is the, pivot point of aerodynamic forces that's based on surface area. So yeah, having a skinnier body has increased our stability and increased our apogee, and we've got a pretty good looking rocket.
Awesome.
Excellent. That's fantastic. Thank you very much, Ben. And Ben's going to go into a lot more details for real knowledge about design next week. He's going to actually be helping you design properly your own rockets. And just some tips while we let you mess around with the software and have a bit of fun, simulate. We want as we said, we want that stability value to be roughly in the range of 1.3 to 2.5. a lower stability value is not desirable. And a few questions you might want to ask yourself while you're messing around with a few variables are diameters. So Ben was just mentioning that the diameter can significantly affect the drag, okay, and the pressure forces. Which nose cone shape is best? Okay, might want to do a bit of research into that. There are definitely different shapes for different purposes. And as we said earlier, is my parachute deploying ideally roughly 1 second after apogee? Okay, we definitely want it deploying after apogee, but not too late after apogee, as Anne and Ben were just explaining. Okay, so I think that's probably a good place to wrap it up, Anne, do you reckon?
Yeah, I reckon. Yeah, so now that we've kind of set you what to expect, you'll have access to 3D printers. Keep that in mind. Access to workshops as well. And we'll be trying to get you guys C65 motors. That can kind of already set like a context to what you're trying to build. So feel free for like up until next week to like do your own, create your own rocket on OpenRocket and just play around with the stuff that you've got. Next week, obviously, we'll be going more, Ben will be going more into detail about what you should be looking for in your specific design. And if you've got things ready, you can definitely show it to us or to Ben and get feedback from him as well. So yeah.
Yeah, I might give a little bit of a taster of what we'll be working towards. So this is an actual example of basically what we just designed. So a 3D printed fin section, the motor goes in the end there. A 3D printed nose cone, it goes on the end, and a parachute on the inside, just made out of rubbish bag, normal everyday components, like, you know, and then like just a cardboard tube I got from Officeworks. This has flown, as you may be able to tell by the battle scars. But yeah, so basically that is what we'll actually be building towards. It'll have to be variable, like, you know, you might be able to find a Pringles can lying around the house or some such. We'll be resourceful. Another example of, you know, the Glad wrap or foil in a tube, etc. So it will vary from person to person. And basically, yeah, we'll be designing a model rocket that'll actually be able to fly using 3D printer and some cardboard tube that you can randomly find around your house, which homework for next week, find the cardboard tube. So yes, now addressing Edwin's question, is the goal to get max apogee? Sometimes. So like, for example, in the actual competition that will be entering the, you know, Australian Universities rocketry competition, which Project Phobos is doing, the goal there is actually accuracy. So we're trying to get as close to exactly 10,000 feet or 3,048 meters as possible. So it's an exercise in, you know, precision engineering. A lot of people do like to just go as high and fast as possible, which also can be quite good fun. In our case, it is basically you're just launching to the conditions. So if you are launching in a park, for example, you don't want to go as high and fast as possible because then you're going to lose it over someone's fence. Ask me how I know. So basically, you want to fine tune your design to, you know, basically fly to a height that isn't going to go crashing into airplanes, fly, you know, high enough that your parachute ejects around apogee, and also low enough that you're not going to lose your rocket, that kind of thing. Does that roughly answer your question?
That's an excellent answer to the question.
Cool. More questions, please. Do we want to like turn off the recording for some?
Yeah, I'm just going to wrap
it
up.
Questions.
So thanks everyone for coming. Feel free to mess around or hang around or head off. And for those of you who are really keen, we'll see you next week where Ben and Hassan will be going to a lot more nitty-gritty details. Again, thanks for coming.
Mm-hmm.